Yeah,
Uh,
recording started.
okay, so should I just begin?
Yeah.
Okay. Good evening, everyone. Thanks for the invite. I'm going to talk about this work that I have with Kyle Lu from Harvard and Jeremy Holland over at Brussels at the Center for Quantum Information and Communication. And this talk is going to be about about mixing times of quantum walks. So I'll explain what these are. I've heard that people here do not necessarily have a background in quantum mechanics, but there's nothing to worry. I mean, all the quantum mechanics that you'll need are contained in the talk, and they're introduced right from scratch. So it should be fine. Okay, so let's begin. So let us begin by this notion of mixing for a classical random walk on a graph. I'm sure many of you have heard of what a random walk is, but just as an introduction, we could consider a simple graph of n vertices and e edges. Then essentially what you have is the random walk is defined by a stochastic matrix P, such that each entry, the ijth entry of the stochastic matrix, is 1 over the degree of the ith node. So essentially what this means is that let us say your graph is regular, right? So every vertex, so degree is essentially, degree of a vertex is essentially the number of nearest neighbors of that particular vertex. And so let us consider a graph where every vertex is connected to the same number of vertices. So in that case, the graph is called a regular graph. So in that case, all these di's are going to be some value d for any I and j. So in that case, what this tells you, this ijth entry of the stochastic matrix, is the probability of transitioning from vertex I to vertex j. So in the case that I mentioned, where the graph is regular, that is where the graph has equal degree, every vertex has the same degree. In that case, if you're at vertex I, you'll just choose any of these vertices that are nearest to this vertex I with a probability 1 over d. That's it. So how does the walk occur? So you can think of the state of a random walk. So essentially the random walk starts somewhere. So the state of the walk, let's say, starts at, say, the walk starts at, say, some vertex. In that case, the state of the walk is just defined by a row vector, where the entry of the row vector just corresponds to the probability of the walker to be in that particular vertex. That's essentially the definition. So for example, if your walk starts at a particular vertex, say this one, then this row vector would be zeros everywhere except at this corresponding vertex where the entry would be 1. So it's just a row vector with entries corresponding to the probability distribution of the walker at that time. So let's say the initial row vector at the start of your walk is some v0, right? So as I mentioned, this v0 could be all zeros except at the vertex where you are, where the corresponding entry is 1. So it could be that, say, for example, if your walk is initialized at, say, a particular vertex of the graph. And the way the walk proceeds is by repeated applications of the stochastic matrix. So if you're at v0, then you apply the stochastic matrix stochastic matrix P, and then you go to v1. So that's the state of your walk after one step. Then you apply P again, and so on. So what happens is that at every step P, you end up with a new distribution over the vertices of this graph. So you end up with a new row vector. And this row vector tells you what the distribution over the graph is at that particular time step, right? So Vt is the distribution of the walker after t steps of the walk, right? So that's as simple as that, the basic definition of a random walk. And what you see is that if you repeat this process, that is, if you apply this matrix P enough number of times to your initial distribution, you converge to a stationary distribution. So So in the limit where t goes to infinity, that you're applying this stochastic matrix many times, you converge to a distribution pi, a special distribution pi. And the reason it's stationary is that the walk, after you reach this distribution, the walk does not evolve anymore. So once you are at this stationary distribution pi, you tend to remain at the stationary distribution pi forever. So in a sense, the stationary distribution is a limiting distribution of your random walk. So you start somewhere with some initial distribution, and then you apply your walk. You do many steps of the walk, and you'll see that you gradually converge to this special stationary distribution pi. And this process is known as mixing. So in a way, because it doesn't matter where you start from, you always converge to this special stationary distribution. So in a sense, you mix the information from where you started from, where the walk started from, is somehow lost. So in that sense, the definition, the term mixing comes from. That's the origin of the definition. And as I mentioned just now, this limiting distribution, the stationary distribution, is independent of where you started the walk from. So this is essentially the definition of mixing on a classical random walk, by a classical random walk on a graph. So let us dig a bit into how much time you would need to mix. So as I told you, you start from, say, some v0. So you start your walk from some initial state, and then you walk, you apply the walk, the stochastic matrix, several times, and you slowly converge. You converge to this stationary distribution pi, right? So what is the mixing time? So what is the time that you needed to converge to a stationary distribution? Well, the definition is given here. It's just telling you that it is the minimum time after which your instantaneous state of the walk, that is the state after, say, some t steps, this capital T steps, is, say, epsilon close to the stationary distribution. So the minimum time after which you are epsilon close to the stationary distribution is the mixing time, is the classical mixing time, right? So I would like to say that, the stationary distribution need not be unique. So you might have a scenario where, the stationary distribution is not unique. For example, if you have graphs that are disconnected, so you have two disconnected graphs, if you start from one component of the graph, you will have a stationary distribution over that component only. And if you start from, say, another connected component of the graph, the stationary distribution would then be basically to the other component. So, but for the cases that we are considering, for example, simple graphs that are, say, non-bipartite, you will have unique stationary distribution. So for the sake of this talk, you can assume that pi is unique. So that's the definition of the mixing time. I reiterate, it's essentially the minimum time beyond which your probability distribution of your walk becomes epsilon close, or comes epsilon close to the stationary distribution. And so how does it relate to the graph, essentially, or the spectral properties of the graph? This is what we are going to see next. By the way, if you have questions, you can just stop me and ask. So suppose, so remember that P was a stochastic matrix.
Hey, I have a question.
Yeah, sure. Go ahead.
So mixing time is independent of which vertex I start from?
Yes, indeed. It is independent. Because the stationary state is, let's say, for these examples that we are taking, is unique, right? So it doesn't matter where you start from, you always converge to that distribution. So it's oblivious to where you start from. In the cases where, the stationary distribution is not unique, then it kind of depends on where you started from. For example, in the example that I gave you, you have two distinct like you have a disconnected graph with two connected components. And so it depends on which component you start from. I mean, the stationary state depends on which component you start from. So in that sense, it has.
But could I take different times to reach? Like, if I chart different vertices, could it be that I take different times to reach the same stationary distribution?
So in the case where the stationary distribution is unique, I'll show you that it really does not depend on where you start from. So the time does not is independent of that. Yeah. So this is what I'm going to talk about right now, actually. So yeah. So I told you that P is a stochastic matrix, right? Because P, the entries of P are essentially the probabilities of transitioning between, say, two nodes. So they sum, the rows, they sum to 1. And so the eigenvalues of P are between -1 and 1. And so what we see is that the mixing time just depends on the gap between the two highest eigenvalues of P. So it's just 1, which is the highest eigenvalue, minus the second highest eigenvalue, delta. And so here I'll use this notation, asymptotic notation. So I am sure all of you know what big O is. So big O tilde is essentially where I'm hiding logarithmic factors. So I'm not going to. So there are some logarithmic factors here that I'm ignoring because the dominant factor is going to be 1 over delta. So this is going to be carried forward throughout the talk. So I'm going to use O tilde, and in all those cases, I would mean that, I'm hiding polylog factors. Okay, so as you see that it just depends on the spectral gap. It depends on the spectral gap of the stochastic matrix, of the matrix that defines your random walk, which is essentially this matrix P. So yes, so these are the two things that I just mentioned. It depends only on the spectral gap, and it is independent of the distribution of the walk curve. So that's all you need to know about classical random walks, classical mixing, and the classical mixing time. So to just recap, it's a classical random walk essentially occurs by the repeated application of a matrix which underlines which is a stochastic matrix, which kind of encodes the connectivity of your underlying graph. And so if you apply this random walk enough number of times, you converge to a stationary distribution, which is oblivious to where you started from, and in that sense you are mixing, right? So this process is called mixing. And then what we just saw is that this mixing happens in a time that just depends on the spectral gap of this underlying stochastic matrix, so the gap between the two highest eigenvalues essentially. Okay, so now we'll move on to what quantum walks are and what quantum mixing time is. But before that, I mean, I'll just give you a very quick introduction to just enough quantum mechanics that you'll need for this talk. I think it'll be self-contained, and I'll give this introduction in a manner where I'll be aware of the fact that we'll be talking about quantum walks. So essentially, I'll introduce quantum mechanics in that respect. So yeah, so whatever I'll present is probably not the most general way of introducing the subject to you, but it will suffice for this talk. So okay, so just as for random walks, you had the state of the underlying random walk. So for quantum walks, and in fact for any quantum system, you can define quantum states, right? So quantum states, they live in what is called a Hilbert space, which is a complex inner product space. And a quantum state is just represented by a column vector. So you had for the classical random walk, you had a row vector representing the state of the classical random walk. Here, I mean, you could have also done the same thing with a column vector for random walks. It doesn't really matter. It's just a matter of notation. But here for quantum states, they are just represented by a column vector, a unit column vector in a Hilbert space. So it's a complex inner product space. So the entries of your quantum state can be complex numbers, right? And yeah, so any n-dimensional quantum state is represented by a column vector of this form, where the entries of this column vector are C1, C2, Cn. And one of the things in quantum mechanics is that any quantum state can be expressed as a linear combinations of other quantum states. So in that sense, it's what the technical term is. It can be expressed as a superposition of other quantum states. So as you can see, I can express this column vector as a linear combination of these individual column vectors, right? So I can label this column vector by the position where the entry 1 is, right? So in that case, it's like C1 times this column vector, C2 times this column vector, Cn times this column vector, right? It's very simple. Now what I call this, so this notation that I mentioned, it's called a ket. It's called a ket. So when I say ket psi, it essentially means this state psi, or ket psi 0. What it means is that it's this column vector psi 0 essentially, right? So this notation is called a ket notation. So there's a bracket notation which people use to write quantum states, quantum operators, these sorts of things. Okay, so any quantum state is just a column vector where the entries are complex numbers, and it can be expressed as a superposition of other quantum states. This representation is not unique here. I mean, you could have other, you could express this as a superposition of other quantum states, but these states, these basis states are kind of special in a way. Okay, first of all, you notice that these are basis space because they span the whole space, and these are the standard basis states. Because I mean, these are somehow, if you have these are somehow known as the computational basis state. So for example, if people have people who have had some introduction to quantum computing, you would know that people, when they talk about quantum computing, when they write down quantum algorithms, this is kind of known as the standard basis or the computational basis. So in that sense, it's special, but any quantum state can be expressed as a superposition of other quantum states, and this representation is not unique. So another way to write this thing is very simple. So you can express this as this form, right? You can express this as a summation of j going from 1 to n, cjj, ket j, but this j now denotes these vectors. I mean, I hope this notation is clear to everyone, right? So what are these? So if you have questions, I mean, please ask. But I mean, this is pretty simple at this moment. So what are these CJs? These entries? Okay, so before that, yeah. So before that, just know that I mentioned that these quantum states are unit column vectors. So these quantum states are normalized. So the way you represent that is essentially take an inner product between this state with itself. And now, because this lives in a complex inner product space or a Hilbert space, the inner product is going to be complex, right? So the way you write this inner product is that you take this ket and you just take the complex conjugate of this ket. So essentially, the way to write that is just the left half of this. So this is what is a ket, and this is what is a bra. So hence the notation is called a bracket notation. So whenever you want to take an overlap between one quantum state with another, you just take the quantum state and you just take the complex conjugate of the other quantum state, and it just get represented this way. So essentially, if you want to take the inner product of psi 0, ket psi 0 with itself, this is what will happen, right? So it's just the mod square of each of these entries, right? So that's essentially it. And because these states are normalized, in a way they are unit column vectors, it follows therefore that the sum of these mod squares of these CJs are just 1, right? So this is another property of quantum states, that they're normalized, right? Okay, so now we come to the fact that what these CJs actually are. So the CJs, they represent what is called a probability amplitude. And what I mean by that is that the probability of psi 0 to be in one of these states is given by the corresponding CJ. So for example, the probability of psi 0 to be in the state ket j is given by the mod square of CJ. So the mod square of the probability amplitudes gives you probabilities, right? So what this means is that quantum states are so if you want to observe actually a quantum system, the quantum system collapses, and what you observe is the collapsed state, and the outcome is probabilistic, of course, because measurement in quantum mechanics is a probabilistic phenomena. And then you observe the corresponding quantum state, the collapsed quantum state, and you do so with a certain probability. So in that case, so in this example, what I mentioned is that if you have ket psi 0, the probability of ket psi 0 to be in this state ket j is given by the mod square of the inner product between j and psi 0. So if you do that, if you take the mod square between any of these j's and psi 0, you just get back cj square, mod cj square. So these overlap, these CJs, these probability amplitudes, they're individually less than 1. And if you sum over these PJs, like we did before, you get that it's 1, essentially, right? So I hope that this is clear to everyone. So these these CJs are just probability amplitudes, and taking the mod square of that, you get probability essentially. So now that we've defined what a quantum state is, the next thing to do is to see how these quantum states evolve, right? So that's the next thing. So just as you had for the classical random walk, you had your initial distribution, you had the initial state of your classical random walk, and your random walk evolved by, say, random applications of a matrix. So so even like if you generalize further, your classical like you take any classical object, if you know its initial state, like say its position, velocity, these things, you know the equations of motion that govern its evolution. If you throw it, or I don't know, if it is in motion, if you know its initial conditions, you can predict its initial final conditions by the equations of motion. Now, what is the corresponding phenomena in what is the corresponding equation in quantum mechanics? Well, that's given by the Schrödinger equation. So it's just saying that, you know, the evolution of any quantum state psi t is just given by the solution to this differential equation. So what does this say? You know, if you have a physical system whose state, as I mentioned previously, is represented by this by ket psi t, which is nothing but this column vector that I mentioned, then, you know, it evolves according to this differential equation, where this h, this quantity h, is some Hermitian matrix. So it's a matrix which is the complex, whose complex conjugate is the matrix itself. So it's a Hermitian matrix, and it kind of for the sake of this talk, you can think of it as some Hermitian matrix that that encodes the structure of the underlying physical system somehow. I mean, in quantum mechanics, this Hermitian matrix gives you, information about the total energy of the system, underlying physical system. But for the sake of this talk, you can think of this as, somehow encoding the structure of your underlying physical system. So in some sense, it is kind of related to, for say, let's say we talk about quantum walks, you can think, loosely that this H is somehow related to the stochastic matrix of the classical random walk P. You can think of it this way, because the stochastic matrix, if it were Hermitian, could have been a Hamiltonian, right? But the equations of motion are different. I mean, quantum equation, like quantum evolution, occurs by the Schrödinger equation, while, classical random walks, if you talk about discrete random walks, it just happens by the repeated applications of, this stochastic matrix P, right? So I've tried to, I've tried to reduce the introduction to very basic levels, and so, I might lose a lot in terms of general introduction to quantum mechanics. So people who actually have read, quantum mechanics and quantum computing, please, please bear with me. I'm just trying to make it as simple and as, to make it as close to classical random walks and quantum walks as possible. This introduction. So yeah. So if you solve this differential equation, what you see is that if you start from, say, some initial state psi 0, then the state that you get after time t is just the solution to this differential equation, where you just exponentiate this Hermitian matrix, which is known as the Hamiltonian. So you just get exponential of minus IHT. So you apply exponential of minus IHT to your initial state, and that you get back a column vector, which is essentially the quantum state after time t. It's as simple as that. Now, if you look at this matrix, so this is just a matrix, right? You're exponentiating a matrix, which gives you another matrix. This matrix is a unitary matrix, right? So because, if you take this matrix times its dagger, I mean, you're going to get identity, right? So exponential of minus IHT times exponential of IHT gives you identity. So quantum evolutions are governed by unitary matrices. So unitary matrices are just rotation. So, you start from some quantum state and you're just rotating to another quantum state. So this is something that you can have, like a geometric picture that you can have in your mind. Okay. So I've talked about quantum states, I've talked about evolutions. Now, how do you see actually physically, how do you observe physically what the entries of quantum states are? I briefly mentioned, how you do that. You make a measurement. So measurement, it's a huge area of research, to measurements can be quite general, but again, I mean, I'll be focusing on a very, very specific case, just enough that you'll require for this talk. So what I'm talking about is that any state that you are in, so if you want to observe that state, you make a observe the entries of that state, you make a measurement in a particular basis. So for example, so what I'm describing is what is known as a projective measurement. So the measurement, it's a kind of measurement where the measurement operators are projections essentially. So for example, if you have the state psi t and you make a measurement in the basis spanned by the states k, some states k, some orthogonal states k. So these could be these states that I just described. So these states k, right? Then the measurement itself, this projective measurement, is defined by this set of measurement operators. It might seem very abstract to you, but I mean, it is. People, lots of experts on quantum mechanics have problems with this measurement, like this problem of measurement. So yeah, for the sake of this talk, think of these as just operators, just matrices, which are just projectors, right? So if you want to measure your quantum system, you just have a corresponding measurement apparatus, which are just projectors. And so if you want to observe the probability of your quantum state to be in some state j, what you do is you just apply this measurement operator mj to your quantum state, right? So mj is just going to be jj, so it's just going to be ket j bra j, and then what you get is essentially the probability of your quantum state to be in this state j. So let's deal with this a bit. So as I mentioned, this ket notation, this is a column vector, this is a row vector, right? So if I take the inner product of just ket k with itself, I'll get back 1, right? So imagine here you put ket j bra j, so what you get here is 1, and in the other half you just get back this, right? So this just this is just the probability of your quantum state after time t, psi t, to be in this state j. That's as simple as that. Okay, so if you had started from say some psi 0, you could have equivalently written expression as bra j, e power exponential of minus iht psi 0 mod square, just from this equation. Just replace what get psi t is here, you'll get the probability essentially. So if you followed this kind of a highly simplified and loose introduction to quantum mechanics, I mean, you will have no problems in understanding what follows. I mean, most of my talk is going to be about just mathematics. I mean, there's very little quantum mechanics involved, so don't worry. Yeah. Okay, so having given that introduction of quantum mechanics, I'll move on to the problem of mixing for quantum walks. So before I begin to talk about mixing of in the quantum scenario, I have to define what quantum walks are. Okay, so the first thing that you notice is that, as I mentioned, quantum evolutions are unitary, right? So you have some initial quantum state and you apply like this matrix exponential of minus iht, which is a unitary matrix. So unitary operations are just rotations, right? So they always preserve distance. They're just rotations. So you never really converge to any limiting distribution, right? So that's one difference. So in the case of a classical random walk, no matter where you started from, you always converged to a limiting stationary distribution. But in the quantum case, you don't. You're just rotating. So in that sense, the definition of mixing in the context of quantum walks becomes slightly more tricky. Okay, so there are two notions of quantum mixing. So one is, you prepare what is called a coherent encoding of the stationary state. So you can think of this as, you had the stationary distribution of your classical random walk. You kind of write a quantum algorithm that prepares a quantum state corresponding to this classical stationary distribution, and you sample from this. So if you prepare this quantum state, this allows you to sample, I mean, from this distribution. But in a way, you are sampling from the limiting distribution of the classical walk and not the quantum walk. And so in a sense, this is not really taking into account the actual mixing of the underlying quantum walk. And it's related to, instead of the mixing time of the classical random walk, it's related to what is known as the hitting time of the classical random walk, which is the time required to hit a particular vertex of your underlying graph. So that's what it is related to. And we've discussed this in length in a different paper of ours. But this is not what we are going to focus on. What we are going to focus on is the fact that you could define a time averaged, in a time average sense, mixing of a quantum walk. I'll come to what I mean by that in the subsequent slides. But the advantage that you have from this definition is that it really allows you to sample from the limiting distribution of the quantum walk, just like in the classical case. In the classical case, you could naturally sample from the limiting distribution, right? Because if you apply the stochastic matrix enough number of times, you reached a limiting distribution, the stationary distribution. In the quantum case, naturally you don't, because quantum evolutions are unitary. But if you define the mixing of a quantum walk in a time average sense, you do converge to a limiting distribution. And so this is what we are going to focus on. And we are going to concentrate also on the continuous version of quantum walks. So quantum walks, just like classical random walks, can be in discrete and in continuous time. For this talk, we'll focus on continuous time quantum walks, but our results will also hold for discrete time quantum walks. Okay.
Hey, just a question.
Yeah.
So
yeah, sure.
I didn't quite get why the quantum walks would never converge. Like, even if the evolution is unitary, it will also have some eigenvector, right?
Oh yeah, so that's a good question. So yeah, of course, in the case where you start from an eigenstate, right, then you'll never evolve, right? So you'll just remain there forever. But I mean, that's essentially like that's a trivial case, right? Because if you start from an eigenstate, you remain there. But if you start from any other quantum state, you'll only reach states, you'll reach states that are distance preserving, right? Because unitary operations are distance preserving, right? So,
Sorry.
Yeah. Okay, so yeah, so we'll focus on continuous time quantum walks. So next I'll define what continuous time quantum walks are, and then I'll define what I mean by this notion of time average mixing of a quantum walk. Okay, so suppose you have a graph of n vertices or n nodes that you label from 1 to n, and you have some e edges. That graph has e edges. How do I define a quantum walk? So for that, first I need to define the state space, right? Because quantum states live in a state space. And the way you do it is each vertex of the graph is a basis element of your Hilbert space. So these states, these ket1, ket2, ket3, ket(n), you could think of these basis states that I had shown you before, where I expressed our state psi 0 as a linear combinations of these states. So this state ket1 is essentially a column vector where you have 1 at the first position and zeros everywhere. N is a quantum state where you have 1 at the nth position and zeros everywhere else. So essentially, a Hilbert space is essentially localized at the vertices of the graph. So the vertices are just basis elements of your Hilbert space. And so you have a graph where vertices are connected to other vertices, right? And so you transition essentially from one vertex to the other according to the laws of quantum mechanics now instead of classical mechanics. Okay. So you for the random walk, you had a matrix which was the stochastic matrix P that defined your random walk. For quantum evolutions, you saw that you had what you called a Hamiltonian, right? So how do you define that Hamiltonian? So for that, I'd introduce what is called the adjacency matrix of any graph. So as I mentioned, for quantum walks also essentially you would need to have a graph, and the adjacency matrix of any graph is just a matrix whose ijth entry is 1 if there's an edge between vertex I and vertex j. It's 0 otherwise. So note that up to now, from what we have defined what the state space of your quantum walk is going to be, right? So now what we'll define is what the Hamiltonian is going to be. So we'll consider that the Hamiltonian, which again is a Hermitian matrix. So in this case, it's symmetric. Adjacency matrix is a symmetric matrix, right? For a simple graph, which is what we are considering. So we'll consider that our Hamiltonian is a normalized adjacency matrix of this graph. So if AG is the adjacency matrix of the graph, then our Hamiltonian is just going to be 1 over the spectral norm times AG. So in that sense, the eigenvalues of AG are between now -1 and 1. So this was done in a way to have an analogy with the classical case. Remember that P in the case of a classical random walk was a stochastic matrix with eigenvalues between -1 and 1. We would like to have fair comparisons with the classical case. So hence, if you divide this adjacency matrix by the spectral norm, you get a matrix whose eigenvalues are again between -1 and 1. Now, so you see that the Hamiltonian of your physical system is just the graph, right? Where the vertices of the graph are the basis elements of your Hilbert space. So you're walking in the vertices of the graph, because your walk takes place in the vertices of the graph. And your Hamiltonian is just the adjacency, a normalized adjacency matrix of the graph. So that your Hamiltonian encodes somehow the structure of the underlying physical system. So this is the thing that I would like you to understand, that it's not just any arbitrary Hamiltonian. It's a Hamiltonian that respects the underlying structure of the graph. It encodes the underlying structure of the graph. So okay, so the eigenvalues of this Hamiltonian, which is the normalized adjacency matrix, are for the notation is such that we'll arrange the eigenvalues in the decreasing order from lambda n to lambda 1, lambda n being the highest, lambda 1 being the lowest, and Vi corresponds to the eigenstate corresponding to the ith eigenvalue. So Vi is an eigenstate corresponding to lambda I, the ith eigenvalue, right? So this is our notation. Okay, so how do you define time average mixing? So quantum walks, just like classical random walks, begin somewhere, right? The walk starts somewhere, right? So the walk, let's say, starts from, say, some initial quantum state now, say denoted by ket psi 0, right? And if you take the actual quantum walk, it's essentially just this, right? So you just start from psi 0, you apply the Schrödinger equation for time t, and this gives you the state of this bit that I'm circling my mouse over, is the state that you get after time t, right? Now, what this says is that, but again, this is unitary, right? So just this bit, e power minus I agt psi 0, you're just applying a unitary matrix, and as I mentioned, you would never really have a mixing process because quantum evolutions naturally are unitary. So what you do is you change the definition slightly of how you define mixing. You define what is called average mixing, and it was introduced by this paper by Aronov, Ambanis, Bazirani, Kempe, and Bazirani, the stock paper from 2001, where they say that you pick a time t that is uniformly at random between 0 and say some capital T, and then evolve this state, your initial state. So this could be, say, this initial state could be localized at a particular vertex of the graph. So then this state would be just 1 at the vertex where you start from and zeros everywhere, right? So that could be your initial state. So starting from this state, you evolve for a time that is chosen uniformly at random between 0 and t, and then you measure in the node basis, like the basis of the vertices, which are just these j's, like these j's, right? This is essentially the basis that they are referring to here. So in that case, since I mean, if you just look at this bit, this gives you the probability of your walk to be in vertex f, right? And now, since your time is uniformly at random, what you get is simply this equation, which is according to the uniform distribution, because you're evolving uniformly at random. And what this pf of t now indicates is your time averaged probability distribution for your walk to be in some vertex f in this case, right? So you start the walk at, so this is how you define average mixing. You start the walk at some initial state psi 0, You evolve for a time that is chosen uniformly at random between 0 and say some capital T, and then you measure at the vertex. So you measure, and then the probability of your walk to be in some vertex F, the time average probability is just given by this equation. Essentially, it's as simple as that. Okay, the advantage that you get from this definition is that you could define a limiting distribution. So if you take limit of t going to infinity, you'll see that this is very well defined. It just depends on the overlaps of your initial state and the final state with the eigenvectors of the underlying Hamiltonian, which is just the normalized adjacency matrix. Right, so this is very well defined. So you do get a limiting distribution from this definition. And what you see is that so this PF of t is just giving you the time average probability after say some time t, right? So this is in a way giving you instantaneous probability time average probability distribution. So naturally you get both. You get the instantaneous probability distribution as well as the limiting distribution. So analogizing with classical random walks, you could also have a definition of a quantum mixing time now. So the quantum mixing time, just like the classical random walk definition, is the minimum time beyond which this instantaneous probability distribution after t steps kind of, or t time, is epsilon close to this limiting distribution, right? So that's the definition of the quantum mixing time, right? So immediately what you see is that so if you just solve this equation and you apply this definition, you get a nice upper bound for the quantum mixing time. Don't worry, it's not very complicated, this expression. So you get a nice upper bound on the quantum mixing time. So you see that you already notice some differences. So you see that this upper bound, so these are just overlaps of your initial state with the various eigenvectors. These are just gaps between the various eigenvalues of your Hamiltonian, which is the adjacency matrix, the normalized adjacency matrix. So you already notice some difference between classical random walks and mixing and quantum walk mixing. The first thing that you notice is that the mixing time, the upper bound of the mixing time, depends on all eigenvalue gaps, not just the spectral gap, as was the case with classical random walk, and also depends on the initial state. So it's not oblivious to where you started from, right? And also this limiting distribution depends on the initial state. So unlike the limiting distribution in the classical case, here you do depend on the initial quantum state that you have, right? So this is the difference. So this is the expression that we are going to focus on. So we're going to focus on quantum mixing times of quantum walks, right? So this is the expression that we are focusing on. So if you look at this expression, so remember that these are just overlaps, right? These are just overlaps, and these are just less than one, right? We saw that individual overlaps, these are just these amplitudes, and they are essentially individually less than one. So what you see is that if you just ignore the numerator for a while, what you see is that to determine this upper bound for the time average, like for the quantum mixing time, what you need is gaps, inverse of the gaps between all eigenvalues, right? So you would need information about gaps between any lambda I plus r minus lambda I. So you would need information about nearest eigenvalues, so not just the spectral gap, but all eigenvalue gaps. So that like nearest eigenvalues, second nearest eigenvalues, third nearest eigenvalues, and so on and so forth, right? Yeah, so if you just forget the numerator for a while, right, because these are less than one anyway, so you can say that the upper bound itself could be obtained by just replacing this as 1, right? So what we actually need to bound is this expression sigma, right, which is this sum, right? So which you could re-express this double sum as these individual sums, where in the first sum we only consider gaps between nearest eigenvalues. Here we consider gaps between second nearest eigenvalues, and so on, right? So in this talk, what we'll consider is that this summation, where we are concerned with nearest eigenvalues, like adjacent eigenvalues, we'll call this some sigma 1, this one sigma 2. So essentially, if we want to bound sigma, what we have is, what we have to bound is the sum over our sigma r's, right, which gives you back this expression, right? Okay, I hope this is clear. Any questions? I mean, you could ask me. Okay, so this is what we need to bound. So we can already see a very trivial, lower and upper bounds for this expression, for this expression. And if you consider that delta mean is the minimum over all these eigenvalue gaps, now of course an obvious lower bound is going to be 1 over delta mean, right? Because you can't do any better. I mean, so your the sum sigma is going to be at least 1 over delta mean, right? Now this sum has n squared terms, right? So in that sense, n square over delta mean is kind of an obvious upper bound for this sum. Now you can show that you can do some work and you can reduce this upper bound to something like O tilde of n over delta mean. So this expression sigma lies between 1 over delta mean and O tilde of n over delta mean, right? So this is what actually this expression on the right hand side gives you an upper bound on the mixing time, quantum mixing time for all graphs, right? Because it's just, this is independent of the graph that you have, like in a sense that the analysis is not graph specific, right? So this gives you an upper bound on the quantum mixing time for all graphs. So this was the result of Ambani, Zaranov, Kempe, Vazirani 2001, and they also showed that for cycles, for example, that the mixing time is in O tilde of n, right? So what we show, our contribution, is that for almost all graphs, this term sigma, this sum sigma, is actually close to 1 over delta mean and not n over delta mean. So what we show is that the upper bound for the quantum mixing time for almost all graphs is actually closer to 1 over delta mean. It's very close to 1 over delta mean. So this is going to be our contribution. Yeah. So what we show is, could we obtain a better upper bound for the quantum mixing time for general classes of graphs? And what we do is we consider what are called Erdös-Renyi random graphs. So I'll explain what these graphs are. So what we showed is that, okay, if you pick up a graph uniformly at random from the set of all graphs, so you have the set of all simple graphs, and you pick a graph uniformly at random, and what we showed is that the mixing time, the quantum mixing time, is in O tilde of n to the 3/2, with a very high probability. That probability that goes to 1 as the number of nodes go to infinity. And for example, if you used the bound of Ambani, Zaranov, Kempe, Vazirani, you would have gotten a mixing time of n to the 7 over 2. So in that sense, it's a polynomial improvement over the bound that they had gotten. So more generally, we obtain a better upper bound on the quantum mixing time for sparse and dense Erdös-Renyi random graphs. So I'll now mention what Erdös-Renyi random graphs are. And one good thing about this random graph model is that if you show that a particular property holds for Erdös-Renyi graphs, you can immediately say that that property holds for almost all graphs, and I'll explain why that is the case. So let us move on to what Erdös-Renyi random graphs are. It's a very simple random graph model defined by Erdős and Renyi in the seminal work in 1959. So consider a graph of n vertices, right? And such that there's an edge between any two vertices with probability p, and this is independent of all other vertices. So between any two vertex, you connect an edge with probability p, right? So each such graph has two parameters that defines it: the number of nodes n and the probability that an edge exists between any two nodes, which is p, right? So hence we denote these graphs as G and P, right? Okay, so consider the case where n is half. So between any two nodes, you toss a coin. Depending on whether it's head or tails, you connect an edge, or you choose to connect an edge, or you don't, right? So this is essentially the same as saying that you're picking a graph uniformly at random from the set of all simple graphs. These are equivalent. The distributions that you'll get are equivalent, right? So what Erdős and Renyi said is that, I mean, they mentioned this in their paper, is that almost all graphs satisfy some property p if Gn half, like this graph, this Erdős-Renyi random graph where p is half, so you're sampling uniformly at random. satisfies this property P with a very high probability. So if Gn half satisfies property P with a very high probability, then almost all graphs satisfy that particular property. So what it means is that the fraction of graphs that satisfy P goes to 1 in the asymptotic limit. So you have the set of all simple graphs. If for example, if P is half, like you're sampling uniformly random right now because P is half, if these graphs they satisfy a particular property, then almost all, but the fraction of graphs that will satisfy this property goes to 1. So so another way of stating this is that the fraction of graphs that won't satisfy this property, or the set of graphs that won't satisfy this property, is a set of measure 0. Right? So when I say almost all graphs, I mean it in this probability theoretic sense. Right? So in the sense that the set of graphs that won't satisfy this property is a set of measure 0. Right? Okay. So this has been well studied. So for example, if P is 1, you have all-to-all connected graph. You have a complete graph. As you decrease P, you'll get sparser and sparser graphs. And what you see is that there are thresholds of P for which the graphs change properties. Like for example, after this value log n over n, if you go below this property, you'll see that the graphs are disconnected. So in that sense, almost all simple graphs are connected, because for P equal to half, you'll get graphs that are connected, right? So this is the random graph model that we'll study. So basically, we'll study the mixing time of quantum walks on these Erdös-Renyi random graphs, and we'll derive a quantum mixing time for these graphs, and then we'll go on to say that the quantum mixing time is this for almost all graphs, right? Now, so throughout the talk, I'll refer to dense Erdös-Renyi graphs and sparse Erdös-Renyi graphs. So whenever P is constant, that is P does not depend on n, so say for P is half or P is 1, I'll call that the graph is dense, of course, because there are many edges connecting the vertices of this graph. And if P goes down with n, as is the case in these two examples, I'll call these as sparse Erdös-Renyi random graphs, right? Okay. So if you notice, the adjacency matrices of these random graphs are random matrices, right? So if you look at the adjacency matrix of this Erdös-Renyi graph, it's a symmetric random matrix where each non-diagonal entry is 1 with probability P, because an edge exists between any two vertex with probability P, and 0 with probability 1 minus P, right? So you're dealing with random matrices, right? Okay, so what we show is that for any P that is greater than n to the minus 1/3, the quantum mixing time is almost surely. So when I say almost surely, I mean probability that goes to 1 as n goes to infinity. It's something in n, it is basically upper bounded by this quantity. So in the case where you have dense Erdös-Renyi graphs where P is a constant, you can show that this is in n to the 3/2 essentially. So if P is constant, this expression is O tilde of n to the 3/2, right? So since that is the case, we can say that almost all graphs, the quantum mixing time on almost all graphs is in O tilde of n to the 3/2, almost surely, right? Okay, so as you notice from the expression for the quantum mixing time, what we need is information about eigenvalues of this random matrix, right? Because we needed to bound the quantum mixing time, we needed information between all eigenvalue gaps, right? So this is what we are going to look into now. So we won't need any more quantum for a lot of the subsequent slides. Now we'll just look at random matrix theory, because all we want to do now, what we've reduced the problem to, is that we need to look at eigenvalues of this random matrix so that we can have information about eigenvalue gaps. And if you have information about the eigenvalue gaps, inverse of that and the summation of that gives us an upper bound for the quantum mixing time, right? Okay, I hope it's clear up to now. You can interrupt me if you wish. Okay, now let's look at the spectral properties, as I mentioned, of the adjacency matrices of Erdös-Renyi graphs. So it is well known that if P is greater than some very small threshold, so if P is greater than log 8 n over n, the maximum eigenvalue of AGNP is a random variable that has a mean NP and standard deviation square root P as in the asymptotic limit. So this was the result by Furedi and Komlos in 1981 and Erdös-Renyi, Zhao and Yin in 2011. So Furedi and Komlos proved it for constant P, so that is for dense Erdös-Renyi graphs. Erdös-Renyi, Zhao and Yin proved it for sparse graphs as well. So already you can see is that, you know, the standard deviation is very, very small, right? So the mean is NP and the standard deviation is square root P of 1 minus P, right? So remember, the Hamiltonian for our quantum walk was the normalized adjacency matrix. So we had to divide the adjacency matrix with the spectral norm, which is essentially in this case NP plus some standard deviation. But what we show in the paper here, we have not detailed here in this slide. What we've showed is that if you divide this adjacency matrix with the mean of the spectral norm, it suffices essentially. So our normalized Hamiltonian now is just AG NP bar, which is just AG NP over NP, right? The mean of the highest eigenvalue of the adjacency matrix of the graph. Okay. Now, yeah, so now we have normalized the spectrum, right? We have so the eigenvalues are now between -1 and 1, right? Because now we have divided by the spectral norm. So let's now look at the second highest eigenvalue. So it is also known from the result of Furedi-Komlos and Van Wu that the second highest eigenvalue is kind of far away from this highest eigenvalue. So, you know, so after normalization, your highest eigenvalue is at 1, right? Now the second highest eigenvalue is upper bounded by something that goes down with square root of NP. So let's say P is constant. This is something like 6 over square root N plus some small like terms, right? So immediately what you see is that the spectral gap, which is the gap between the two highest eigenvalues, is just omega of 1, like a constant, right? So since the classical mixing time depends on the spectral gap, you can immediately conclude that the classical mixing time is quite fast. It's an octilde of 1, right? But remember that for the quantum mixing time, all gaps are crucial. So we need information about all eigenvalue gaps, in fact, all eigenvalues, and not just, you know, the spectral gap, right? So for that, we need to look at the bulk of the spectrum of these random matrices, of the adjacency matrices of these random, of these Erdös-Renyi graphs, right? So what we have is for the bulk of the spectrum, what we have is the so-called Wigner semicircle law. So this is well known that the bulk of the spectrum of AGNP in the limit where NP goes to infinity converges to a semicircle distribution. So if you look at this expression, it's a semicircle with some radius, right? There's a semicircle distribution with certain radius. So what does this actually mean? It means that, okay, so this is the radius of the semicircle of AGNP. So this is the distribution of the eigenvalues in the bulk of AGNP, right? Of the adjacency matrix of the Erdös-Renyi graph. Now, for our case, we are normalizing the spectrum, right? So we are dividing by NP, right? So the radius will now shrink. So if you divide the radius by NP, you'll get something like this as the radius, right? So something that goes down with 1 over square root NP, right? So what does the semicircle distribution actually mean? That, you know, that that the bulk of the spectrum converges to a semicircle distribution. What it means is that just divide so take a line between -r and r, divide that interval into small bins, and count the number of eigenvalues in each bin. So do a histogram analysis, and what you will see is that the distribution that you get converges to a semicircle. So that's essentially what the semicircle Wigner semicircle law tells us, right? That the distribution of the eigenvalues of the adjacency matrices of this random matrix converges to a semicircle with this radius, right? Okay. So what else does the semicircle law tell us? So it tells us that for any interval I, so if you want to find the fraction of the eigenvalues in any interval of AGNP, It's just given by the area of the semicircle plus some error like that goes down with n, right? So this is one thing that the semicircle law tells us. The other thing that the semicircle law tells us is that so it's called the classical eigenvalue location. So this is nothing to with classical physics, quantum physics. It's just a definition. A classical eigenvalue location is just a definition. Okay, so for any eigenvalue lambda I of A, G, and P, the corresponding classical eigenvalue, which we'll denote by gamma I, is just given by the solution of this equation, right? So what this means is that if you are looking for the ith classical eigenvalue, fill up I over n area of the semicircle. That's where the ith classical eigenvalue is going to be, right? Okay, so these are the two things that the semicircle law can tell us, right? It is known, it is well known that the actual eigenvalues from the semicircle law itself, you can show that the actual eigenvalues are close to the classical eigenvalues, right? So in a way that lambda I is equal to gamma I plus some small o of 1, right, with a very high probability. So the actual eigenvalues are close to the classical eigenvalues. It's the first thing. Now, how close they are is what we'll be interested in. So what the semicircle law tells you is that macroscopically, I'll explain what I mean by macroscopically in a minute. Macroscopically, each eigenvalue should be close to their classical location. But the reason it is macroscopic is because this works only when the interval under consideration is very large. So only when we are looking at eigenvalues that are far apart, when this interval is quite large, does this work. So for example, this small o of 1 error term, it doesn't go down sufficiently large, sufficiently fast. So for example, since we are interested in all gaps, including gaps between consecutive eigenvalues, so where the size of the interval would scale as something like 1 over n, the semicircle law is useless if you're looking at gaps between these intervals. Like if you're looking to, if you're analyzing, eigenvalue gaps within this interval, like such small intervals, the semicircle law is useless. So what would we need from the semicircle law if it can't give us information about distant like eigenvalue gaps between various like adjacent eigenvalue gaps, for example? What would we need it for? Well, we'd need it for two things, right? So the first thing that the semicircle law can tell you is what the average eigenvalue gap is. So you know that the radius of the semicircle is something like 1 over square root np, right? We saw that in the previous slide. And there are order n eigenvalues lying within the semicircle, right? So you divide n over, like you do 1 over n times 1 over square root of np, you get this, which is essentially the average eigenvalue gap. And what you can also get from the semicircle law just by solving this equation is some information about the distance between the classical eigenvalue locations. So you can actually lower bound the distance between the classical eigenvalues. So these are the two things that we'll take forward in the talk. Distance. So from the semicircle law, we have information of the average eigenvalue gap, which scales as something like 1 over n to the power 3/2 square root of p. And we also got information about the distance between the classical eigenvalue locations. Okay. So clearly, if you want to look at eigenvalues that are kind of close to each other, like something where this does not hold, the interval is kind of smaller, then we can't look at macroscopic statistics of eigenvalues of random matrices. We have to go to mesoscopic. We have to go to mesoscopic scales, right? So at mesoscopic scales, there's this result which kind of tells you that actually, even if you go to finer scales, so you had the macroscopic scale. Now, if you go to finer scales, the actual eigenvalues are again concentrated around the classical eigenvalues. So this is what is known as the eigenvalue rigidity criterion. The formally it's just it was just given by Erdös-Renyi Erdös-Yao and Yin in 2011 and Erdös-Yao and Yin in 2013, where they showed that as long as p is greater than n to the minus 1/3, you don't need to care about the exact expression. All this says is that, you know, lambda I minus gamma I is kind of closed. That is, this error kind of goes down fast, right? The reason I call this mesoscopic is that you can go to, you know, finer scales. So the global semicircle law could only talk about, you know, would only give you information about gaps between eigenvalues that are very, very far apart. Here they show that the semicircle law also holds at, you know, local level, kind of locally. So in a way you can go to, you know, finer scales at a mesoscopic level. But even eigenvalue rigidity does not provide information about the smallest gaps. That if you're really looking at, you know, eigenvalues that are like that are next to each other, like consecutive eigenvalues, eigenvalue rigidity criteria fails. And the reason, and you know, you can have this nice picture that tells you why these things fail, is because if you look at you know, if you look at the top line, the black stripes represent the actual eigenvalue locations, and the red stripes represent, you know, the corresponding classical eigenvalue location. So if you're looking at eigenvalues that are far apart, right? So if you want to calculate lambda I plus r minus lambda I, let's say where r is large, right? You see that they are well approximated by gamma I plus r minus gamma I. So in a way, when you're looking at eigenvalues that are far apart, eigenvalue rigidity criterion can act as a very good approximation of the distance between the actual eigenvalues. But however, if you zoom in and you look at consecutive eigenvalue gaps, you may have a situation where the actual eigenvalues are much, much more close to each other than the classical eigenvalues. And so in a way, even mesoscopic statistics of eigenvalues are not good enough. So what you need to do, so if you really want information about the closest gaps, then you need to look at microscopic statistics. But we'll make use of eigenvalue rigidity when we are, you know, having to look at eigenvalues that are far apart. But when we are really looking at eigenvalues that are close to each other, like adjacent eigenvalues, then we need to go to microscopic statistics of, you know, eigenvalues of these random graphs. But remember, I mean, just to recap, we need information about all eigenvalue gaps, right? So eigenvalues that are far apart, eigenvalues that are very close to each other. So we'll see later on that we'll use also mesoscopic statistics of eigenvalues, that is the eigenvalue rigidity criteria, as well as, you know, microscopic statistics when we are talking about very, very close eigenvalues. Okay, so let's now look at the microscopic statistics of eigenvalues, right? So what about, yeah, essentially, what about bounds on consecutive eigenvalue gaps? So when you're looking at, say, these delta i's, right, where delta I is just lambda I plus 1 minus lambda I, so just adjacent eigenvalue. These are extremely difficult problems in random matrix theory. For example, you know, this question of whether, you know, the minimum of these eigenvalue gaps was 0 or not. That is, if the spectrum of eigenvalues of a random graph is simple in a way, that is, there are no degeneracies in the spectrum, you know, asking whether that is the case was open for a very long time, right? And in fact, Tao and Wu in 2014 showed that, you know, AG and P bar, that is A bar G and P, that is the adjacency matrices, the normalized adjacency matrix of an Erdös-Renyi graph, has a simple spectrum for dense graphs almost surely. That means that if you have a dense Erdös-Renyi random graph, all the eigenvalues are distinct. There are no degeneracies with a very high probability. And this was extended to sparse Erdös-Renyi random graphs by Liu and Wu in 2018. In fact, not only this, Nguyen, Tao, and Wu in 2015, they showed that these delta i's are not just, you know, not non-zero, they are kind of separated. And what they did was they obtained tail bounds on these delta i's. So what they showed is what they wanted to show is how likely are these delta i's to be delta times less than the average gap. Remember, we could obtain the average gap from the semicircle law itself, which was something like 1 over n to the power 3/2 square root of p. So what Nguyen, Tao, and Wu they asked is, how likely is each delta I to be delta times less than the average. So this is what the result is, and I don't know, it essentially gives a bound on the supremum of this probability. The supremum of the probability that each of these delta i's is less than is less than delta times the average gap is bounded by this quantity, right? With a very high probability. Okay, so what this does is, as soon as you get the supremum of these probabilities, what you can do is you can just apply a union bound very trivially. I mean, just like very straightforward, that just applying the union bound to this gives you like an information about a lower bound on the minimum eigenvalue gap, right? So minimum of all eigenvalue gaps you can show is lower bounded by n to the 5/2 plus small o of 1 square root of p. I mean, this is once you get this is easy to obtain, right? But these are extremely challenging problems in general. Like, for example, this result, like obtaining microscopic statistics, information about each adjacent eigenvalues, are extremely notorious problems in random matrix theory. Okay, so we have information about the microscopic statistics as well, where we could obtain a lower bound for the minimum of all eigenvalue gaps, right? So remember that to upper bound the quantum mixing time, we needed to obtain an expression for this double sum, and this sum sigma, we could obtain a lower bound and an upper bound, right? And what we'll show is that for sigma, the sigma for Erdös-Renyi random graphs is actually very close to 1 over delta mu, right? This is what we'll show. Okay, how do we do that? So we'll start by upper bounding sigma 1. Remember, sigma 1 was where we were just looking at adjacent eigenvalues. So we'll prove that this is upper bounded by this quantity. This is the first thing we'll do with a very high probability, almost surely, essentially. The way we do it is, I'm not going to show you the whole proof, but the intuition behind this is that you count how many of these delta i's are close to the average. And what we'll show is that if you take an interval that is 1 over, say, some 1 over log to the power 4 times the average, you get a constant factor, a constant fraction of all the eigenvalues within this interval. So you just count the number of eigenvalues that are close to the average, and this is how you get a bound, an upper bound on sigma 1. So if you look, if you remember what the lower bound for the minimum of all the eigenvalues were so if you notice what this delta mean, the minimum overall eigenvalue gaps was, you could see that this upper bound is 1 over this delta mean, the lower bound that we had obtained. So in that sense, sigma 1 is close to 1 over delta mean, but we need to obtain an upper bound for sigma, not just sigma 1, right? So how do we do it? So we saw that sigma 1 is close to 1 over delta mean, right? It's upper bounded by the lower bound for 1 over delta mean. So what about sigma? So upper bounding sigma, we use two things. So first, we use the distance between the classical eigenvalue locations that we had gotten from the semicircle law. And second, we use eigenvalue rigidity. So we use eigenvalue rigidity, which told you that at the mesoscopic level, eigenvalues are like the actual eigenvalues are close to the classical eigenvalues. They're classical eigenvalue locations, right? So what is the strategy that we use? It's the strategy that we use is very simple. When you're looking at small values of R, that is when you're looking at eigenvalues that are very close to each other, you can't use eigenvalue rigidity, right? Because it doesn't hold anymore. So what you do is you look at the microscopic statistics, where you have the tail bounds for these delta i's, at the microscopic level. So you use this for eigenvalues that are very close to each other, while for eigenvalues that are far apart, you make use of eigenvalue rigidity, because what eigenvalue rigidity tells you is that if you go to large enough R, that is, we are looking at eigenvalues that are far apart, you can pretty well replace the actual eigenvalue gaps with the classical eigenvalue gaps, right? You remember this diagram I showed, which I'll show you in a little while. So basically, that's the idea. So for small values of R, when the eigenvalues are very close to each other, we use the tail bound on delta I. So we use the microscopic statistics, and for large values of R, so when R is far apart, you just replace lambda I plus R minus lambda I with gamma I plus R minus gamma I. And so when can we do this? We can do this when, the error, uh, when this quantity, like the distance between the classical locations, is larger than the error due to these quantities, right? So in that case, you can exploit eigenvalue rigidity, the fact that you can replace lambda I plus R minus lambda I with gamma I plus R minus gamma I, right? And what we show is that this happens for a critical value of R. That is, if you're looking at eigenvalues that are closer than this critical value, then you can't use eigenvalue rigidity anymore. But for R that is greater than this R star, you can exploit rigidity. So this is kind of the strategy that we use to derive sigma. So what we do is exactly what I said. So what we prove is that if P is greater than n to the minus 1/3, we prove that sigma is upper bounded by this quantity. And what you can immediately see is that if P is constant, you get that this is something like n to the 5/2 plus small o of 1, right? Which is not far from what the lower bound for the minimum eigenvalue gap was. So again, I'll come to that in a while, but the proof strategy is what I mentioned. So you split this sum into two parts. So in the first part, what you do is you only consider eigenvalue gaps that are less than R star, right? So in that case, you use the microscopic statistics which you had used to derive the upper bound on sigma 1. So you just replace this as R star times sigma 1, like that's an obvious upper bound. And when you look at eigenvalue gaps that are kind of far apart, like further than this R star, you just use rigidity and replace lambda I plus R minus lambda I with the lower bound for gamma I plus R minus gamma I. So this gives you this expression, right? So what you see is that if you have dense Erdös-Renyi random, so you get this upper bound. So if you, again, as I mentioned, if you look at dense graphs, that is when P is constant, you see that sigma is close to 1 over delta min, the lower bound for 1 over delta min, right? Okay. Now, so there was one thing remaining, right? So up to now we had spoken about the upper bound for the quantum mixing time. But what is the quantum walk going to mix to? What is the limiting distribution? Well, for that we had this expression, right? The overlaps, like mod square of the overlaps between the initial state and the eigenvectors, as well as the final state and the eigenvectors, right? So what we show is that we use another kind of result from random matrix theory, which states that the eigenvectors for the Erdös-Renyi random graph, for the adjacency matrix of Erdös-Renyi graphs, these eigenvectors are delocalized, completely delocalized. That is, the infinity norm of these ket VIs is upper bounded by something that is n to the minus half plus small o of 1. So in that case, if you just replace this quantity, so because f is just a vertex, right? So f would have 1 at the fth entry and zeros everywhere, right? So it just, you can take this out. This will be something like 1 over n, right? Because it's a mod square. And then this is just a sum of probabilities, right? So what you get is that this limit pf of t going to infinity, the limiting distribution is O tilde of 1 over n. So in that sense, the limiting distribution is very close to a uniform distribution. Doesn't matter where you start from. So irrespective of where you started from, you converge to a uniform distribution, right? Okay, so now you look at the full expression for the upper bound. So now you know that the limiting distribution is uniform. The next thing for the quantum mixing time, we had evaluated these sums, but for the actual mixing time expression, remember we had these overlap factors. But now we could use the fact that so if you start from, say, some localized vertex, these quantities from this delocalization property of the eigenvectors are just 1 over square root n up to some log factor. 1 over square root n, this is also 1 over square root n, so you get a 1 over n outside. So you get 1 over n outside times this sum sigma, right? The double sum that we had represented by sigma. So this helps us, reduce the upper bound further. So you get something like O tilde of n to the 3/2, right? Instead of the exponent being 5/2, you divide by n and you get something like 3/2, right? Okay, so which gives you kind of the full expression for the quantum mixing time. Remember that this holds for any p greater than n to the minus 1/3, because eigenvalue rigidity holds for n to the minus 1/3 for p greater than n to the minus 1/3. So this kind of summarizes our results. So for example, for dense Erdös-Renyi graphs, you have this as the mixing time, n to the 3/2, O tilde of n to the 3/2. For sparser graphs, you get this mixing time, upper bound for the quantum mixing time. And for even sparser graphs, I mean, you can't use eigenvalue rigidity. So what you do is you just make use of the microscopic statistics, and then you just replace n times the result by n times the what you get from the microscopic statistics, because rigidity does not hold for such sparse graphs. So we can't exploit rigidity anymore. Anyway, so what we did was we improved the upper bound on the quantum mixing time for almost all graphs. So that was our contribution. And as I mentioned, that for sparser and sparser graphs, that is if p is greater than log 8 n over n, we can't use eigenvalue rigidity, and so we get slightly weaker upper bound for the quantum mixing time. Anyway, so I would like to talk about some ongoing and future work very fast, but could any of you tell me how much time I have? I mean, I've probably far exceeded the time, I guess. So could you tell me how much time I have? Any of you?
Usually we end in like 1 hour, but that's not an issue. We've gone over time before.
Okay. So
Since it's
let's
recorded anyway, people who need to drop out can just watch the recording, so it'll be fine.
Yeah, sure. Okay. Okay, so anyway, I'll just briefly mention some of the applications that these results could have. For example, many of these results that I've mentioned for the adjacency matrices of Erdös-Renyi graphs, they hold for Wigner matrices in general. So Wigner matrices are more general in the sense that these are random matrices where each entry is a discrete random variable. So these are Wigner matrices. They find applications in several areas of physics. So many of these results they hold for Wigner random matrices. So one other scenario where this could be extended to is something called band Wigner matrices, which are essentially Wigner matrices such that these are symmetric Hermitian random matrices where you have each entry is 0 other than within a band of the diagonal, and within this band you have random entries. So these are these band Wigner matrices. So we could extend we could attempt to extend many of these results for band Wigner matrices, something that I'm working with currently with Kyle Lu and Vishesh Jain at Stanford. We could also, many of these results could have applications in other areas of physics. For example, if you want to find upper bounds on the equilibration times of isolated quantum systems. So for example, quantum systems, they never really isolated quantum systems again evolve unitarily, they never really equilibrate. But for example, if you again define it in a time average sense, and after some time you want to find the expectation value of some observable, what you see is that what matters is, instead of eigenvalue gaps, what matters is the gaps of eigenvalue gaps. So many of these results could be useful for improving the upper bounds for equilibration times for quantum systems that are defined by random Hamiltonians. Okay, the other thing that I would like to mention is that randomized time evolution, this notion of time averaged mixing that where I mentioned a randomized time evolution where you pick a time that is uniformly at random between 0 and t. These could be used to leverage to improve several quantum walk based algorithms. For example, there are these glue trees algorithms by Childs et al. From 2003, which had a running time of n to the 5. So they basically find, so there you have like two binary trees that are glued together by random connections, and you start from one end of the binary tree and you have to reach the other end. What Childs showed is that for this problem relative to an oracle, you get kind of an exponential speed up. In the case of a quantum walk, you need something like order of n to the 5 time for a quantum walk, but whereas for a classical random walk you need exponentially longer time. But what we showed is that you could actually improve the running time of Childs et al. To something like O tilde of n square by harnessing the spectrum of the underlying blue trees algorithm. There's some other ongoing work with my collaborators in Brussels. I'm not going to go into the details of them because I far exceeded the time, but they are to do with the relationship between discrete time quantum walks and continuous time quantum walks, which have been open for a very long time, and it's essentially, you know, finding a very general relationship between you know, the underlying graph and, you know, the hitting time by a quantum walk. You know, what is the relationship between discrete time quantum walks and continuous time quantum walk? Some of these questions, which are very clear in the classical scenario, are not so clear in the quantum case. So we are currently working on some of these problems. So thank you for your patience. Thank you for listening, and I apologize for, you know, exceeding the stipulated time. Lastly, I'd like to mention that I'd be joining the institute as a faculty at the beginning of next month. So in case you want to, you know, chat with any of these topics, feel free to drop me an email. Yeah, thank you.
Are there any questions?
Hi, so thank you
Hi.
for the talk. So yeah, I think after the Wigner semicircle now I was a bit lost, but yeah, I have like on whatever I understood, I have one or two questions. For a random matrix, what does it mean? Like to ask, is delta min 0?
Well, so in the sense, so for example, you ask whether with a very high probability
Okay.
you have that the spectrum of the underlying random matrix, is it like all the eigenvalues are distinct or not? That's essentially what you're asking, right? Just so the minimum eigenvalue is also going to be a random variable, right?
Right.
Minimum
Yeah.
of all eigenvalues. So is it going to be something that is 0 plus some fluctuations, like mean 0 plus some fluctuations, or it's going to be some quantity that, or you can lower bound by that by some quantity, which you know, Tao and Wu and later on other people, they showed that is indeed the case, you know.
Okay.
Yeah.
Yeah, and like one more thing. So those special graphs that you took, the Erdös-Renyi graphs, where it's sufficient to show some property for say all graphs G n comma half, and if you show that property, so you need to take all possible graphs that you can get G n. No.
Yeah. So what I mentioned there is that so if you take Gn half, right,
Yeah.
and you show a certain property holds, like for example, let's say, is your graph connected or not, let's say, right? So if it holds for Gn half, then the fraction of graphs or the set of graphs that don't satisfy this property is a set of measures 0.
So G n half is a set. So G n half is a distribution where like every graph has some probability to be in Gn.
Yeah, so it's a uniform. So it's essentially you're sampling uniformly at random from the set of all graphs. That's what Gn half tells you.
Okay, and what does it mean to show that a property holds for Gn half?
So it means that so for example, this is what it means. Like for example, you pick a graph uniformly at random, right? Is that graph connected or not? You analyze whether the graph that you get, is it almost surely connected or not, right? If it's connected, then you can straight away say that, okay, it's connected for Gn half. Hence the fraction of graphs for which, you know, this is like, so if you sample from the set of all graphs, you're highly likely to get a connected graph. That's what it means. So for example, in our case, for the quantum mixing time, what it means is that if you sample uniformly random from the set of all graphs, then it is highly likely that the mixing, so if you pick a graph uniformly at random, it is highly likely that the mixing time of quantum walk on this graph is going to be upper bounded by O tilde of n to the 3 half. This is what it means.
Okay. So do you need to say that if you pick a graph uniformly at random with a high probability, this probability goes?
Yeah, like a probability that goes to 1 as n goes to infinity. Yeah.
Okay. Yeah. Yeah. Thank you. That's it. Yeah.
Thanks.
Okay, so if there are no more questions, I'll stop recording.